Swayam Prabha. Digital India. Educated India.
Right? So I use both those facts. So now I got a smaller tree of k nodes, and I can apply my induction hypothesis. Okay? So any two nodes in G prime, I know has a unique path in G prime. Okay? So now let's prove that for any two nodes UV in G, there is a unique path. So let's pick any two UV. Suppose U and V are both different from W. Then so we just argued this in the previous slide also, any UV path in G is present in G prime. This is what kept G prime connected because W cannot occur in the middle of a path. And therefore, for these UVs, any path in G. So first of all, there is a path in G prime by induction hypothesis. There is exactly one path in G prime. So that path will be present in G. And there cannot be any other path in G, because if it were there, it would have been there in G prime too. But G prime has exactly one path. So by induction hypothesis, G prime has exactly one path, and we just argued G cannot have any more paths. G would also have just that one path between U and V. So this is for the case when U and V are both different from W. What if one of them is equal to W? Say V equals W. So then, of course, there is no path in G prime from U to W, but any path in G from U to W should be of the form. So remember what a path is. It's a sequence of nodes, U0, U1, U2, and so forth, ending in W, and any adjacent pair is connected by an edge. But what can appear just before W? The only thing that can appear just before W has to be a neighbor of W. W has only one neighbor. Let's call it X. Right? So W, since it's of degree, it's a leaf, it's of degree 1. It has exactly one neighbor. Let's call it X. So any UW path will look like a UX path followed by W. Okay, so that's the list of nodes in any UW path. And how many such paths are there? Well, there is exactly one UX path. We already argued that here, right? So there is exactly one UX path, and then there can be only one UW path. So that's the case when one of the nodes, say in this case V equals W, same argument holds for when U equal to W and V not equal to W. The only remaining case is when U and V are both W, in which case there's only so there is a trivial path of length 0, and WW paths, there can be only one by definition of a path. You cannot have a longer path from W to W. It won't be a path. It will be a cycle. Okay, so that's a simple inductive argument to show that every pair of nodes like this has a unique path. But it's also an illustration of how you would use induction on trees by deleting leaves. Okay, so that's the end of that proof. Let me show you one more example before finishing. So this is about the number of edges in a tree. Again, it's a very useful property, and it's also a very simple illustration of this inductive argument. So the claim is that in a tree with n nodes, so V is a set of vertices. Suppose the size of that set is n, so it has n nodes. Then the number of edges is exactly n minus 1. Doesn't matter how complicated the tree looks. If it is a tree, it has exactly n minus 1 edges. If it's a tree with n nodes, it has to have exactly n minus 1 edges, irrespective of how the nodes are connected together. Okay, so it's a very useful property, and let's prove it by induction on the size of the tree, the number of nodes. Okay, so the base case again, the case of single node, there is only one such tree, there are no edges in it, so indeed the number of edges is 1 minus 1. For the induction step, again we'll use weak induction. Suppose for all k greater than or equal to 1, you have for any k greater than or equal to 1, suppose you have shown that the hypothesis holds for trees with k nodes. So the number of edges is the number of vertices minus 1. We'd like to prove the same for an arbitrary tree with k plus 1 nodes. Okay, and so given such a tree, what do? We simply pick a leaf and delete it and get a new tree. And we can apply the induction hypothesis to the new tree. So for the new tree, the number of nodes, the number of edges is its number of nodes. So it has k nodes minus 1. So its number of edges is k minus 1. And comparing it with the tree we started with, there is exactly one extra edge because what we deleted was a leaf. It has only one edge incident on it that got deleted and going from G to G prime. So E has exactly one more edge compared to E prime. So the size of the number of edges in E is K, which is the number of nodes minus 1. So there's nothing much going on here, just saying that by ordering, by considering your tree, by deleting one leaf at a time, you keep shrinking your tree, and at each point you're deleting one node and one edge until you get to the point where there's only one node and no edges left. So the number of nodes is exactly one more than the number of edges. Okay, so it's a very simple argument, but it's a very useful fact. And there are a bunch of other useful conclusions you can immediately draw from this. For instance, suppose I give you a graph which is connected and which has a right number of edges. So the number of edges is one less than the number of nodes. Then the only way this can happen is that it must be a tree, right? So clearly, if it is a tree, this holds. That's what we proved in the previous slide. And here it's saying if it's connected and there's the right number of edges, then it must be a tree. So why is that the case? Suppose not. Suppose it was not a tree. So that means it's connected to be not a tree. It has to have some a cycle. Okay, so somewhere in the graph there is a cycle. If that's the case, I can delete any edge in this cycle and keep the graph connected. So why is that? Suppose there was some, so the graph originally is connected, so between any pair of nodes you can find a path, but some of these paths might be passing through this edge that I'm going to delete. So when I delete this path, no more x's. Still, I'm claiming that this graph would be connected because you can go around this cycle, and so after you come here, instead of taking this edge, you go around the cycle and come to the other point and continue with your path. And in the process, what you get is not going to be a path anymore. It could be a walk, right? In this example, you retrace this edge. So it's a walk, but it is still, it still shows that these two edges are connected to each other. Okay, so it remains a connected graph. Okay, so if there is a cycle, I can delete an edge and still stay connected. And if there is still more cycles, I keep repeating this until there are no more cycles. And throughout, I kept the graph connected. So, and I did not delete any vertices. So I have ended up with a connected graph of with no cycle, so it's a tree. And the number of edges is whatever I started with, and then whatever number of edges I deleted. I deleted at least one edge here, so I will have number of edges strictly less than what I started with. Okay, and that is a contradiction, because in a tree you should have number of edges equal to number of nodes minus one. Okay, so so that is that proves this. Also, here's another claim. If I took a tree and added an edge to it, then it'll have a cycle. Okay, it has to have a cycle now because it's still connected. If it doesn't have a cycle, it'll have to be a tree. But since I added an edge, it no more satisfies this relation, so it cannot be a tree. So it has to have a cycle. And in fact, it should have a single cycle. You should think this through. If adding an edge could in principle create a lot of cycles. There could be a lot of cycles that can use a newly created edge. But if I'm adding this edge to something that was a tree, something which didn't already have any cycles, then I could have introduced at most one cycle. And one way to think about it is, suppose I introduce two different cycles, and there is at least one edge which is present in one cycle and not in the other cycle, and then I delete that edge, I will get a connected graph with the right number of edges, and therefore it will have to be a tree from what we just now said. But we just said, this edge I deleted is not present in another cycle, so that cycle would still be intact. So this will not be a tree, and that's a contradiction, right? So there can be only one cycle. Okay, that's, we are talking about number of edges in a tree. What about number of edges in a forest? That depends on the number of connected components. This relation here extends to the following. The number of connected components is the gap between the number of vertices and the number of edges. So for the case when it's a tree, so this is 1, right? The number of vertices is 1 more than the number of edges. If you have many components, then in each component there will be a gap of 1. So altogether there will be a gap of as many components as there. Okay, so this is just saying the same thing again. You write your graph in terms of the various connected components, the disjoint union of various connected components, and in each connected component it holds that EI, the size of EI is size of EI minus 1. So altogether, over all the connected components, you have the size of V is the size of V minus the number of connected components. Okay. And one last thing, so what happens when you delete a node from a tree? So we talked about when you delete a leaf, it remains a tree. What if I deleted some other node which is not a leaf? And that depends on the number of or the degree of that node. So if I delete a node of degree D, then this tree breaks down into a forest with D connected components. Okay, so if D was 1, then the tree remains a tree. That's what we saw. When the leaf is when the node is a leaf, then the tree will remain a tree. So it'll have one connected component. But in general, so here's a node in the tree. It has degree 4 here. If I delete this node and the edges incident on it, I'll be left with 4 connected components, right? And that'll be, how do you see that without drawing a picture? Here, when you delete the node, the size of V goes down by 1 and size of E goes down by D. So the gap goes up by D minus 1. Okay, So the number of connected components increases by d minus 1. Originally it was 1, and now it will be d. Okay? So that's what happens when you delete an arbitrary node in a tree. Okay, that's it for now. You will keep coming across a lot of applications of trees, especially in as data structures, and also as a way to simplify graphs by you know, considering a tree structure, a tree subgraph, for instance, of a graph. Okay, so trees are very important, and you will keep coming across them in all of computer science. Today we'll talk about an interesting result called Dilworth's theorem. To put it in context, we have seen a few results of a type that I would call MinMax results. And in particular, last time we saw that there is a relation between sizes of matchings and sizes of vertex covers. Namely, any matching gives a lower bound on the size of every possible vertex covered. So this was a pictorial illustration of that. So this was a simple observation that a vertex cover will have to devote a vertex to cover each edge in a matching. A same vertex cannot be used to cover two edges in a matching. So this was a simple observation. But then there was an interesting result that said that actually this is tight, at least in the case of bipartite graph. So Koenig's theorem said that the size of the largest matching, in fact, equals the size of the smallest vertex cover. Another similar result we saw some time back was Mirsky's theorem, which related the sizes of chains in a poset with the sizes of anti-chain decomposition. So partitioning the ground set into anti-chains. So how many anti-chains do you need? And again, there was an easy relation saying that if you have a large chain, then every anti-chain decomposition will have to be at least as large as that. And that's simply because the anti-chain decomposition will have to devote a separate anti-chain for each element in the chain. You cannot have two elements in the chain appear within the same anti-chain. Okay, and this was called, so this was a simple observation, but then it was there was a tighter relation saying that in fact equality is achieved. There is a chain and an anti-chain decomposition which are of the same size. So the size of the largest chain in fact equals the size of the smallest anti-chain decomposition. What we'll see today is a very similar result, which similar to Mirsky's theorem. It just swaps chains with anti-chains. So you'll have size of any anti-chain is a lower bound, so it's an easy observation that size of any anti-chain is a lower bound on the size of any chain decomposition for the same reason. And what is interesting is that, again, equality can be achieved. The size of the largest anti-chain equals the size of the smallest chain decomposition. Okay, so again, the one direction is easy in this equality that the size of anti-chains is a lower bound on the size of chain decomposition for the same reason as in the case of Mirsky's theorem, that an anti-chain and a chain can have an intersection of size at most 1. So for every element in the anti-chain, the chain decomposition will have to spend a separate chain on it. Okay, so you cannot use the same chain to cover two elements in an anti-chain. Okay? So that direction is easy, that chain decompositions will have to be large. It will have to accommodate each element in this anti-chain, so the largest anti-chain, in separate chains. What is interesting and what we will see today is the other direction, and that forms the sense of Dilworth's theorem. Okay, so that's a little theorem again. The least number of chains needed to partition S is exactly the size of a largest anti-chain. And as you saw, one direction is easy. So what we are going to prove now is the other direction, that in fact there exists an anti-chain whose size is as large as the size of some chain decomposition, and that would be the smallest chain decomposition. Okay. How are you going to do that? Here is a plan. First, we'll construct. So we're given some poset, right? And n is the size of the ground set. Let's say, and I'll use this symbol. I'll just call it less than or equal to as the poset relation. We'll construct a bipartite graph with the following properties. So if you give me a vertex cover, a small vertex cover in this bipartite graph, that would translate to a large anti-chain in the poset. Okay? In particular, if you give me a vertex cover of size t, it would translate to an anti-chain of size at least n minus t. Also, if you give me a large matching in this graph, that would translate to a chain decomposition into a few chains, into a small number of chains, in particular n minus t chains. Okay, so why do I want to do that? Suppose you manage to prove this, then you have translated this question in Deleuze's theorem into chains and chain decompositions and anti-chains into something about vertex covers and matchings. And this is something we, in a bipartite graph, and this is something we know more about. We can use Koenig's theorem to relate the two. We can say by Koenig's theorem that in any bipartite graph, and in particular in this bipartite graph, there is a vertex cover and a matching of the same size, okay, say size t. Then that would imply that there is an anti-chain of size at least n minus t, and there's a chain decomposition of size at most n minus t. So there is an anti-chain which is at least as large as some chain decomposition. And that's what we wanted to prove, that there is an anti-chain which is at least as large as some chain decomposition. Here the size happens to be n minus t. Okay. So what remains to be done is to prove these two facts, that there is a bipartite graph with these two properties. So here is the bipartite graph that we want to construct. It's simply the two parts are have elements from the ground set, but there are two different copies of it. So I indicate it as for each element in S, I have a node u comma 0 that's in the left part, and u comma 1 that will be in my right part. And I put an edge between u comma 0 and v comma 1 if u is related to v, so u less than or equal to v, and u and v are not the same. So even though it's a reflexive relation, I do not put edges between u comma 0 and u comma 1. I put an edge between u comma 0 and v comma 1, where u not equal to v and u is related to v. Okay. So that's my bipartite graph. So here is an example. So this has a diagram of some relation. So D is related to B and C. B and C are related to A. And by transitivity, D is also related to A. But the Hesse diagram doesn't show it. And if I were to draw the bipartite graph here corresponding to ABCD, I have A0, B0, C0, D0 on the left, and A1, B1, C1, D1 on the right. And corresponding to, say, the edge DC here, I have D0 to C1, similarly D0 to B1, and the relation that D is related to A translates to the edge D0 to A1. Okay? And similarly, A1, everything is related to A1, so you have the other edges, B0, C0, both are connected to A1. And those are the only edges in this example. Okay, so that's my bipartite graph on which I'm going to make this argument that its vertex covers and matchings are related to the chains and anti-chain the chain decompositions and anti-chains in the graph. Okay, so let's start with the vertex cover. So suppose you're given a vertex cover. Okay, so here is an example in this. So D0 and A1 together forms a vertex cover. Okay? And happens to be the smallest vertex cover. Okay? But given any vertex cover C, I'm going to define a set obtained. You could think of it as by squishing together the two parts of the graph. So I'll drop the distinction between the left copy and the right copy of each element in S, and just collect all the elements, whether if U0 or U1 occurs in C, I will collect it into my set B. Okay, so in this example, so C was D0 and A1, B is just going to be D and A. Okay? If D0 and D1 were to appear in C, there will be only one copy of D in B. Okay, so B is obtained by ignoring the distinction between the left nodes and the right nodes, treating them just as elements in S. So B is a subset of S. I'll also define A, which is all the elements in S which are not in B, so the complement of B. Okay. So it is this A that I'll be interested in. So first of all, I'm going to claim that this A is large. How large? If I give you a vertex cover of size at most T, then clearly B is less than or equal to T because I only identified various elements in B, pairs of elements in B into one element. So the size of going from C to B, the size could have only shrunk. So B is less than or equal to C, and A is simply A is equal to S minus B, size of S minus size of B. So it's greater than or equal to size of S minus size of C. So if C is less than or equal to T, then A is greater than or equal to N minus T. Okay, all right. So A is greater than or equal to size N minus T, and further, it is an anti-chain. Okay? So why is it an anti-chain? Well, suppose if it were not, what does that mean? There are some two elements U and V which are related. Okay? In particular, there is an edge from U0 to V1, right? That will be an edge because U and V are related and U not equal to V. There are two distinct elements. However, neither U0 nor V1 is part of C. If they were part of C, then if say U0 was part of C, then U would have been part of B, and then it cannot be in A, right? So both these, U and V were left out of B because U0 or U1 for that matter, and V0, V1 are not part of the vertex cover. But then we have a contradiction. It cannot be a vertex cover. Here is an edge U0 V1, and neither of its endpoints are included in this vertex cover. Okay. All right. So this is the first thing we want to say. If you give me a vertex cover, a small vertex cover, then that would correspond to a large anti-chain. So smaller C gets, B also gets smaller, and my set A gets larger, right? So if you give me a small vertex cover, I will give you a small vertex cover in this graph G, I will give you a large anti-chain in the poset. Here's the second thing I wanted to say. It's about matchings. So suppose I give you a large matching. Okay, so I give you some matching M. My goal is to find a small chain decomposition. Okay, decomposition of a small number of chains. So how am I going to get my chains? So suppose the matching M given is M. I'm going to define a graph F. Again, essentially I'm going to squish together the two copies of the two parts of the bipartite graph. And I'll define a new graph over just S, right? The ground set S. And my edges are, if there was an edge U0, V1 in the matching, then that would translate to an edge UV in my new graph. Okay, so suppose there's a matching. From it only has B0A1 and D0B1. When I construct my graph F, I have only 4 elements, the A, B, C, D, right, which I've drawn here, A, B, C, D. And what are the edges? There will be an edge between B and A. There will be an edge between D and B. Okay, so B and A, D and B. So these will be the two edges. Okay, and there is an isolated vertex. I'm claiming that actually, if you look at it, it's in terms of the poset, this is a chain. Okay, and this is also a chain, and this is going to be our chain decomposition. Okay? So let's see, in general, why that should be the case. So first of all, I claim that this graph F is a forest. That means each connected component is a tree, but it's a little more than that. In fact, each connected component in F is a path. Okay, so how do I know that? So first of all, I claim that any node in F will have degree at most 2. Why is that? Because what is an edge? What is an edge in the graph F? So if you have an edge UV, then either you should have an edge U0 V1 in M or an edge V0 U1 in M. But you cannot have, say, U0 V1 and another U0 W1 in M because M is a matching. So U0, the node U0 cannot have two edges incident on it. Okay, so if I have, say, in this case, D is D has an edge, in E star. Well, it can have two edges in E star, one corresponding to D0 and another corresponding to D1, edges in the matching if they exist. But that's it. You cannot have more than two edges. Okay. And it's not just that there are two edges, it's also that, if you have two edges and one of them, the corresponding copy of the node U will be on the left and another will be on the right. Okay? And therefore, in one of them, the relation would be U less than or equal to V for some V, and in the other, it will be, say, W less than or equal to U for some U. Okay? All right, so I know that every node has degree at most 2. Graphs in which every node has degree at most 2 actually do already decompose into where each connected component has this property. So a connected component could be an isolated vertex, or it could be a path, or it could be a cycle. Okay. However, in F, I claim that there cannot be any cycles. So what if there was a cycle V0 up to Vk? Well, from just what we argued just now, suppose you order this cycle such that orient cycle such that V0 is less than or equal to V1, related like this. And from what we just argued, I know that the edge between V1 and V2, it cannot again be of the form V2 is less than or equal to V1. It has to be of the form V1 is less than or equal to V2. Okay. Otherwise, if you had V0 less than or equal to V1 and V2 less than or equal to V1, then it would be the right-hand copy of V1 that will have two edges in the matching, which it cannot. So we know that if you have V1 has degree 2, then it's of this kind. V0 is less than or equal to V1 and V1 is less than or equal to V2. and then V2 is less than or equal to V3, and so forth, until you get to Vk is connected to V0, so Vk is less than or equal to V0 because already V0 is less than or equal to V1. But that is a contradiction because now you have, remember, a partially ordered set doesn't have any cycles. It is because it is anti-symmetric, it cannot have any cycles. So you cannot have a cycle in the pose set. Okay, so that would be the contradiction. All right, so I have a forest, and F has degree 2 and no cycles. That makes it a forest where each connected component is a path, potentially a path of length 0. Okay, and I claim that each such connected component, each path, is actually a chain in the pose. Again, for the same reason, right? When I was arguing here, if I have a path V0, V1 up to Vk, suppose it was not a cycle, just a path, then I would have this relation V0 less than or equal to V1 less than or equal to up to Vk, and that by definition is a chain in the pose set. Okay? So each path in this forest is a chain. Each connected component is a chain. Okay, so that's nice. What I wanted to argue, though, is that it's not that I have a chain decomposition, but I want to argue that I have a small chain decomposition. If the matching is large, there are a lot of edges here. So there are a lot of edges in the graph that I obtain. Right? Every edge here appears as an edge in the graph F. Right? So it has a lot of edges. I want to argue that it has a small number of connected components. But I do know this because there is a relation between number of edges and number of connected components in a forest. Okay? So the gap between, so the number of connected components is exactly the number of, is the gap between the number of vertices and the number of edges. And the number of edges we just now argued, every vertex in the matching shows up as an edge in this graph. So it's exactly S minus M. So in particular, if my matching is of size greater than or equal to T, the number of connected components or the number of chains in this partition of the poset is less than or equal to N minus T. Okay. Okay, so that completes the construction of the bipartite graph with these two properties. And as we already discussed, that applying Koenig's theorem to this bipartite graphs gives you Dilworth's theorem. Okay. Actually, it's useful to think of Mirsky's theorem and Dilworth's theorem, which sound very similar to each other, as some sort of as dual problems, right? And one way to see that duality, how they are related to each other, is by looking at them as results about the comparison graph of a poset. So what's a comparison graph? It's what you would expect it to be. Given a poset, you construct a graph in which the vertices are the elements in the poset, and you put an edge between u and v if u and v are comparable. If u is less than or equal to v, or v is less than or equal to u, it's an undirected graph, and you omit, you do not put any self-flows. Okay? So it's essentially the graph you would get by squishing together the bipartite graph that we talked about earlier. Okay, and one useful thing to remember about a comparison graph is if I, so if I took a poset and simply restrict it to a subset of the poset, and I'll still get a poset, right? It will still be a transitive, antisymmetric, reflexive relation. And you can get the comparison graph for this smaller poset by simply restricting the original graph to a smaller set of vertices and retaining all the edges that remain within that set of vertices. So that is the induced subgraph of the original graph. Okay, so the induced subgraph any induced subgraph of a comparison graph is also a comparison graph corresponding to the poset that is obtained simply by restricting to the corresponding smaller subset of the ground set. Okay, to start relating or to start seeing Mirsky's theorem and Dilworth's theorem in terms of the comparison graph, so what does a chain in the poset look like? Well, remember, a chain means any two elements are comparable to each other. So in terms of the comparison graph, that simply means it's a clique. It's a subset of vertices such that any two vertices have an edge between them. Okay, so it's a clique. It's a complete connected subgraph in G. And what is an anti-chain? It's there are no edges between any two elements. No two elements are comparable, so it corresponds to an independent set, or equivalently a clique in the complement of G. And so that's what a chain and an anti-chain are. What does a chain decomposition and anti-chain decomposition correspond to? So what is an anti-chain decomposition? So each, imagine, so anti-chain decomposition, a bunch of anti-chains, right? And each anti-chain, we said, is an independent set. So imagine coloring each anti-chain with a color. It would give you a valid coloring because there are no edges within the same color set. Each color set is an independent set. Okay, so that would be a valid coloring of the graph. So an anti-chain decomposition corresponds to a valid coloring of the graph, and the size of the decomposition, namely the number of anti-chains you need, is exactly the size of the number of colors you need, right? And if there's a one-to-one correspondence, right? Any coloring corresponds to an anti-chain decomposition. So it's exactly the same thing, coloring G or partitioning the poset into anti-chains. And similarly, a chain decomposition so it corresponds to coloring of the complement of G. So you want to, or you could think of it as a decomposition into cliques, right? So of G, if in terms of G complement, there's again a decomposition into independent sets, which is what a coloring is, right? So a chain decomposition is simply a coloring of G complement. Now let's restate Mirsky's theorem and Dilworth's theorem in terms of this. So Mirsky's theorem says, if you give me a poset, look at its comparison graph. So give me an arbitrary comparison graph G. The size, the chromatic number of G, which is to say the smallest number of colors you need to color G, which is the smallest anti-chain decomposition of the poset, is exactly the same as the clique number of G. So that's the clique number of G is the size of a chain, right? The largest chain. So the largest chain is the same as the number of anti-chains you need to decompose a graph, right? So clearly, again, and now you see that one direction was easy. So if you have a large clique, you need a large number of colors. So chi G is greater than or equal to omega G is the easy direction, and that's true for every graph. What Mirsky's theorem says is that if the graph is a comparison graph, then actually an equality holds. And what about Dilworth's theorem that we just now saw? Dilworth's theorem is about the complement of a comparison graph. So it talked about a chain decomposition, which is a coloring of G prime. So the smallest number of colors you need to color G prime, that's the smallest chain decomposition of the poset, is equal to the largest anti-chain, the largest clique in G prime. So that's a clique number of G prime. So again, one direction was easy, that was saying chi g prime is greater than or equal to omega g prime. And what we just now showed was that, in fact, the equality holds chi g prime equal to omega g prime if G is a comparison graph. Okay, and to see both these results as duals of each other, of course they are already looking quite similar. They're statements about G or G complement, the same statement where G is a comparison graph, right? But you can go a little further and see why both of these results should hold if one of them holds. And that's by thinking in terms of considering the notion of what's called a perfect graph. Okay? So definition of a perfect graph is that so this equality holds, chi g equal to omega g holds, but not just for the graph, but for every induced subgraph. Okay? So a perfect graph is one in which for every induced subgraph G prime, the chromatic number and the clique number are equal. So restated now, Mirsky's theorem is simply saying a comparison graph is perfect, and Delva's theorem is saying the complement of a comparison graph is perfect. As it turns out, there is a very non-trivial result called the perfect graph theorem, which says that a graph is perfect if and only if its complement is perfect. So, and we know a lot, by now we know a lot more about perfect graphs. We know exactly which graphs are perfect, and this perfect graph theorem is an easy consequence of the characterization of a perfect graph. But so, of course, we are not going to prove this perfect graph theorem. It's quite non-trivial. However, given the perfect graph theorem, and then you can see that Mirsky's theorem and Delva's theorem are, they imply each other directly, right? So because Mirsky's theorem says a comparison graph is perfect, and now you take its complement, by perfect graph theorem, that's also perfect. So therefore the complement of a comparison graph is perfect. And that's Dilworth's theorem, and conversely from Dilworth's theorem we can go to Mirsky's theorem. So that we will, that's all we will do for now, but just a pointer to other deeper relations and interesting properties of graphs that you will probably come across later on.